Welcome back. Right about now in the class, things can feel a little bit overwhelming. You just learned a bunch of different derivative rules, and while I like to imagine that you learn them perfectly every time, usually you need practice, and more than that, you need practice in a different environment where you don't know which rules and which derivatives to use, because it's really different when you know what section you're in, and you know this is the section for the chain rule, and so I will be using chain rules. So the purpose of this quick aside is to give you a minute to catch your breath and practice, but also in a way where I'm not going to tell you ahead of time which rule to use. So sometimes this is its own section. I'm just going to do this in one kind of long video with 6 different examples. And in each one, you got to figure out what to do and do your best. And hopefully you pause the video and give it a try before I go through them. All right, hopefully you tried. Here I go again. These were all intentionally picked not to be the most complicated, but examples of the chain product and quotient rule. This first one, I hope you realize, is a quotient. So if I want to take the derivative, I take the derivative of the top, which is negative sine of x. Then I leave the bottom alone, minus leave the top alone. And I take the derivative of the bottom, which is in this case is just a 1. Feel free to leave those brackets empty and go back and fill them in if you need to. I'm assuming we're getting a little faster. On bottom, I have the bottom squared, and that's just x squared. You could most definitely simplify this a bit. In fact, maybe I will for old time's sake. It looks like this would be negative sine of x. Oops. Times x, we usually write that x out front. So negative x sine x minus cosine of x all over x squared. Often the way we'd write this is actually to pull that minus out entirely and just write a negative out front of the whole thing because they're both minus. You could also split this up into 2 fractions and let one of those x's cancel for the sine of x. Great. Looks pretty good. This next one might not be so obvious that this is a chain rule problem, because we know how to get the derivative of 10 to the stuff. The derivative of 10 to the stuff is natural log of 10 times 10 to the stuff. But in this case, that's a 5x. And so we want that whole thing times the derivative of stuff. The derivative of 5x in this case is just a 5. That's it. We could try to write this a little cleaner if we want to. 5 times natural log of 10 times 10 to the 5x. That's not a whole lot cleaner. And that's about as clean as it gets. This might be a good time for you to practice simplifying just to make sure, if nothing else, you know when to stop. You know when there's really nothing else you can do, or when there is something you can do. So I know I often don't simplify, but maybe practice this time around. Okay, let's go ahead and move on to our next one. This looks like a product rule. I've got 2 functions multiplying each other. So if I were to looks like I want the derivative of the first one, leave the second alone, plus, notice plus for product rule, minus for quotient rule. Then I leave the first one alone, and I take the derivative of the second. We'll see if you remember that derivative. So the derivative of x to the 3 halves, the 3 halves comes down, and then I subtract 1. 3 halves minus 1 is 1 half. You could, of course, write that as a square root. This is also equal to 3 halves times the square root of x. X to the 3 halves times the derivative of tangent x. The derivative of tangent is secant squared of x. Yeah, it would be nice if you remembered sine, cosine, and tangent. It would be nice if you knew all of them, but those 3 people usually try to remember. Okay, we could clean this up. We could factor something out if we wanted to. If I want to be really, really silly about this, I don't think this is that much better, but sure, why not? Let's go ahead. We can pull out an x to the 1 half. And if I pull out an x to the 1 half, that's a square root of x times, looks like I get 3 halves tangent of x, plus, if I pulled out x to the 1 half, what is left for the second term? Looks like x to the 1, so that is just x secant squared of x. It's a little better, certainly a little nicer. All right, and there's not much I can do with that. Okay, so it is important that you are able to both remember all these little derivatives of the functions, but also identify when is it product, quotient, or tangent rule. Next up, ones where we might need to do multiple rules. And some of these, there is more than one way to do it correctly. So it's possible that you'll do it differently than me. But I have an intended way in mind, which is really just to go straight forward with it. So take a minute and see if you can figure these out. They might take a little bit more work because they might take more than one rule. I'm going to count to 3 in my head, and then I'm going to start. All right, hopefully you paused it. You took a minute. Here's me starting. So the first thing I see here is this product. The outermost thing I see is the product. And that's how I want to think about it. It's from the outside in. So the outermost thing is this product. So I do my product rule. It's going to be the derivative of the first thing. I leave the second alone. By the way, this x over 2 pi, you see that a lot because we're just changing the period. The period was a 2 pi, and then we're gonna change that to make the period 1. So we're just rescaling that horizontally. I'm going to do a plus. I'm going to leave the e to the x alone. And I'm going to do the derivative of the second thing, and I'll give myself some room for that. Because looking ahead, I can see the derivative of my sine of x over 2 pi is going to require a chain rule to get that. All right, so these brackets can really help you out. Do this piece by piece. The derivative of e to the x, I hope you know, is e to the x. Hooray. That's our favorite derivative. Now I have to do a chain rule with this sine of x business. So looks like the derivative of sine of stuff is cosine of that same stuff. But now I need the derivative of that inside. And that the derivative of x over 2 pi, sometimes right about now people start getting tripped up by this. X over 2 pi is equal to 1 over 2 pi times x. So the x becomes a 1, and this just becomes 1 over 2 pi. Or thought of differently, just divide the whole thing by 2 pi. All right, I'm going to clean this up just because that's what we're doing today. So I can factor out that e to the x, and then I get a sine x over 2 pi and then I get a plus, looks like 1 over 2 pi, or you could just divide by 2 pi, cosine of x over 2 pi. Another parentheses. Nice. A little nicer. A little easier to understand what's happening, I think, if I write it like that. And in the end, that's our goal, right? Our goal is to communicate. And to communicate clearly. Okay, next up, you can see this take a little bit more space. The biggest, most outermost thing I see is a quotient. So I'm going to start following the quotient rule. I'm going to give myself lots of space here for this first derivative. And then I leave the second alone. And then I do a minus, and I leave the square root alone. And then I take the derivative of times the derivative of my second. You notice I often cap my square roots. I feel like it makes it really clear where it ends. Otherwise, especially with all this multiplication, it can get quite confusing. Okay, all over this whole denominator squared. I really don't think there's another good way to do these first two here, number 4 and 5. I think really the way I'm doing is the only way I can see that will get me through. Okay, so my square root is really to the 1/2. And so I'm going to write this as bringing the 1/2 down, 2x plus 1, and then to the negative 1/2, because 1/2 minus 1 is negative 1/2. And now I still need to multiply by the derivative of the inner function. The derivative of 2x plus 1 is a 2. Nice. And on my second one, I need the derivative of x squared plus 1. That is just 2x plus 0. Ta-da! That's about it. I might skip simplifying this one. There's a little bit, right? The 2 and the 1/2 are going to cancel, which is really nice, and I can pull out that 2, but sure, let's go ahead. We'll write it a little nicer. The 2 and the 1/2 are going to cancel. I could pull out, yeah, there aren't really great ways to write this. I could do some silly things like pulling out that square root. So maybe I won't, and I'll just write this as 2x plus 1 times x squared plus 1 minus 2x root 2x plus 1 over, I could FOIL this out, but I actually like it factored a lot more. Don't FOIL things out if you don't need to. I know sometimes it helps with those derivatives to multiply things out. That might be the only thing you could really do, is if you multiplied out this denominator, maybe it would change how you took the derivative, but you get something equivalent. And we like factored denominators. Okay, several other ways you could write that, but it doesn't get too much better than this. You could, yeah, that's really about it. All right, last one. Looks like we have a lot going on. So the biggest thing I have on this last one, the outermost function I have going on is a division. There's definitely more than one way through this. One thing you might do that I think is actually a pretty good idea is to multiply out that that x to the -1 and x. So I'll show you that in a second. But let's just do this the longest way, and then I'll maybe show you another way. So if I take the derivative of the top is going to be a lot of work for us. I might even need more room. So let's just focus on the derivative of the top for a second. If I do my product rule inside of that, I would get, looks like negative x to the -2 plus 1, and I leave the secant alone, plus I leave this alone. I do need more room. I take the derivative of secant, which is secant x tangent x. Whew, that's the derivative of the top. Leave the bottom alone, because now I'm back in this quotient rule. And I subtract, I leave the top alone. So I'll do a big bracket here. X to the -1 plus x, secant of x. And I take the derivative of the bottom, which is just e to the x, all over e to the x squared. Remember, e to the x, all parentheses, squared is the same as e to the 2x. Whew, pretty long. That simplifies quite a bit. I'm not going to. So e to the x's will cancel, which is great, but I'm not going to worry about it right now because it takes a long time to write. But let's just show you there is another way of doing this, which is to first do algebra. And the algebra I might do first is just this. X to the -1 secant of x plus x secant of x all over e to the x. This may or may not feel easier to you. I feel like the derivative of the top is a little bit more straightforward if I rewrite it like this by multiplying it out. Oftentimes multiplying it out makes things easier. You could even, if you wanted to, let's just keep going here, I could write this as secant of x, x to the -1 just brings it to the denominator, plus x secant of x e to the x. And for a lot of people, especially when they're starting out, this way of writing it is going to feel better because it means you can do them separately. It's just a little bit less you have to remember to do in your head. So multiplying out numerators and splitting that fraction can be a really nice way of making sure that you're able to follow your work more nicely. Maybe the last point I'd make is that what you get out might not look exactly the same, especially if you have trig functions involved. It might not immediately look the same as your neighbor, and you might still have the right answer. You might both just have really different ways of writing the same thing. And this is one of the reasons why, some algebra skills to see are they equivalent, or some trig skills to see are they equivalent, are so necessary to do well in calculus. Okay, that's it for now. Practice some more. This skill of doing multiple in a row and just identifying which one to do is almost its own skill that it's worth taking a minute to practice and find some more problems for. All right, I'll catch you next time.